Hello everyone, welcome to Final Summative for Applied Business Analytics course. My name is Gajanan Naule and I am student of AlmaBetter Data Science course. So as the task was given, we were supposed to select 50 questions and answer them in well-structured format, considering the introduction first, then step-by-step explanation, and then finally conclusion. So I have selected those 50 questions out of 80 questions. And out of these 50 questions, I will be presenting five most critical questions in this video. And all these concepts are those which come up in almost every real world business scenario. So moving to the questions, these are those questions that I have selected. So first is, what is the difference between correlation and causation? Second is, what are type 1 and type 2 errors in hypothesis testing? Third is, what is bias theorem and how it is used? Fourth is, how do you detect and treat outliers in dataset? And fifth and final question is, how is hypothesis testing utilizing A/B testing for marketing campaigns? So let us move to our first question, which is, what is the difference between correlation and causation? So our first question is, what is the difference between correlation and causation? So let me explain you correlation first. So what is correlation? Correlation simply means that two variables tend to move together. If variable A goes up, variable B goes up. On the other hand, causation is much stronger. It means that variable A is causing B to change. So we constantly see things are correlated and we jump to the conclusion that one is causing the other. So that's not always the case. So let me walk you through some traps. First is confounding variable, which is hidden factor. So what is that? Let me tell you the example. So take an example of ice cream sales and shark attacks. So if you look at the data from beach towns, you will see nearly a positive correlation between ice cream sales and shark attacks. So now someone would look at the data and say, let's ban ice creams. That will save the sea mars. But is that right? No. Why? Because ice cream doesn't attracting any sharks. The real cause is a confounding factor, which is weather. So what is happening in hot weathers? People buy more ice cream. People also go more oftenly to swim in ocean. So ice cream didn't causing any attack, but the weather, which is a hidden factor, that drove both numbers up. So trap number two is spurious correlation. So what is spurious correlation? So this is when two things are correlated by total coincidence or historically. So for decades in Europe, data showed that towns with more storks had more babies. So this actually is where the fairy tale is came from, which is that storks deliver babies. So was it true? No. The hidden link here was house size. So rich families had bigger houses. Storks like to nest on bigger roofs. So rich families also tended to have more babies or larger families. So stars and babies were correlated but totally unrelated. Third factor is the reverse causality. So reverse causality is, let me give you the example. So imagine you are analyzing sales team. You notice a huge correlation that high performing sales people spend more time on CRM software. So you as a manager might look at that and say the software causes more success. So we need to force software on low performing individuals. But will that change anything? No. Why? Because it is actually the reverse thing, which is reverse causality. The top performers are already motivated, well organized, successful. Because they are well organized, they naturally choose the software to track their deals. And the software didn't make any successful change. But if you force a bad salesperson, that will not change anything, because it is actually the people who are already successful. They are tend to use software more. Uh, So why the difference between correlation and causation matters? So imagine if you see customers use discount codes. So and you started assuming that the discounts are making people customers cheap. So let's stop the discounts. If you do that, you will lose your sales. Why? Because it is far more likely that the budget conscious people who naturally demand discounts are the ones applying coupons. So if you remove the discount code, instead of fixing the customer, you will lose your sales. That is why knowing the difference between correlation and causation is very important. Okay, so next question is what are type 1 and type 2 errors in hypothesis testing? So in real world, statistics is about probability and not certainty. Whenever we make a decision based on data, there is a risk we are wrong. We categorize these mistakes into two specific types. To understand them, we first have to remember what null hypothesis is. Null hypothesis is default result or assumption like this person is innocent, this patient is healthy, this email is safe. Let us understand type 1 and type 2 error by an example. Think of an courtroom. In trial, the null hypothesis is the defendant is innocent. We need evidence to prove otherwise. So first is a type 1 error. So this is false positive. This happens when we reject a null hypothesis or primary assumption, even though it was actually true. So in the courtroom, this is convicting an innocent person. The jury look at the evidence, they decide guilty, but they were wrong. They found an effect guilt where there wasn't one. Second is type 2 error. This is false negative. So this happens when we fail to reject the null hypothesis, even though it was false. In the courtroom, this is letting a guilty person go free. Evidence wasn't strong enough, so the jury said not guilty. But they missed the truth. So, which error is worse? The answer depends on the cost. So, let us see two cases. First is case one, which is a spam filter on mailbox. So, uh, null hypothesis is email is safe. So here type 1 error is blocking a really important email from your boss. Second is type 2 error. This is letting spam email get through. This is annoying, but this is still fine. So verdict is we minimize type 1 errors. We rather see spam than lose a real important email. So case B is quality control for airbags. So suppose we are selling airbags. So null hypothesis is airbag is working fine. So here type 1 error is throwing away a working airbag because we suspect a fault. This costs money. Money is wasted. But in type 2 error is putting a broken airbag into a car. This costs lives. So verdict is we minimize type 2 errors. We don't care about wasting few good units, but we absolutely cannot lose lives. So there is no fixed answer to this that which error is worse. As an analyst, it is our job to decide which risk the business can afford. So next question is what is Bayes theorem and how it is used. So Bayes theorem describes the probability of an event based on prior knowledge of conditions that might be related to the event. So to explain this, I want you to visualize a manufacturing plant with two machines. Let's call them machine A and machine B. So if you look into this image, so there are two machines. One is machine A and machine B. So machine A is our main workhorse. It is massive. It produces almost 90% of our total output. It is high quality machine with very low defect rate of only 1%. On the other hand, we have a small machine B. So machine B is an old machine. We use it as a backup machine. It is tiny. It only produces 10% of our output. So it is unreliable and it also has a defect rate of 5%. So Here is the test. Imagine I walk into a factory floor and I pick up a random part of the conveyor belt and I see that it is defective. So the question is, which machine did this broken part came from? So you might probably say that it came from machine B. And why? Because machine B is the bad machine. It breaks the stuff all the time. That is what a bad analyst would think. They focus only on the error rate. But a Bayesian analyst uses the base rate, which is the sheer volume that machine A is producing. So let's say we are producing a batch of 1,000 parts. So machine A makes 90% of them, which means it is producing 900 parts. And with 1% defect rate, it is producing 9 broken parts. And machine B is producing 100 parts. And with 5% defect rate, it is producing 5 broken parts. So now there are 9 broken parts from the good machine, which is machine A. And there are 5 broken parts from machine B, which is bad machine. So if you are holding a broken part in your hand, it is actually almost twice as likely to have come from machine A. And why? Because machine A is so massive that even its tiny 1% error produces total garbage more than a small machine. So the conclusion here is that Bayesian theorem is critical for strategy. If you find the manager of machine B because he produces all the defects and you try to fire him, so you would be making a mistake. Why? Because most of your defects part are coming from machine A and not machine B. So simply because of the volume, machine A is producing more defective parts. So Bayes' theorem teaches us that we cannot judge probability on just one factor. We have to look at the whole picture. So and the formula for a Bayes theorem is probability of A given B is equal to probability of B given A into probability of A upon probability of B, where probability of B is not equals to 0. So next question is, how do you detect and treat outliers in dataset? So an outlier is simply a data point that is drastically different from rest of your dataset. Identifying and handling them is crucial step in data cleaning because they can distort statistical analysis. So detection. We can detect them in two main ways. First is using a box plot. So here is a box plot. So box plot is the most common method. Outliers appear as individual dots floating outside the whiskers of the plot. So here you can see there are three boxes and all these are data points. So all the data points that are lying inside the box are within the interquartile range, and all that are lying outside the box uh, that are out of interquartile range. And those who are outside the box and are too far from rest of the data points are called as outliers, like this one. So the second is mathematically using interquartile range rule. So we calculate interquartile range as quarter 3 minus quarter 1, which means the data that falls under quarter 3 minus quarter 1. So any data point falling more than 1.5 times the interquartile below Q1 or above Q3 is flagged as an outlier. So anything that falls under 1.5x of Q1, which is this, is outlier, and above 1.5x of Q3 is outlier. So these are outliers. So to explain this clearly, let's look at the call center scenario. Imagine you are analyzing the performance of call support team. You look at the data for 10 calls. 9 of those customers had great experience. They were answered exactly in 1 minute. Uh, but one customer had a terrible experience. They got lost in the system and waited for 61 minutes. So now, if you report this to the management, if you calculate the mean, you add up all of them, which becomes 9 plus 61 is equal to 70, and divide by 10. The result will be 7 minutes. So if you tell that to your boss, the average wait time is 7 minutes. He will think that the whole team is slow, and he might try to fix the problem that doesn't even exist. But if you calculate the mean, the answer becomes 1. Why? Because one is the outlier. One of those cases are outlier. So this example shows us two things. First is the mean is very sensitive, and second is in this case, the median tells us the team is doing good job, but the outlier tells us we have a broken system that trapped one poor person for an hour. So if you just look at the average, we would have missed that specific glitch that caused the problem. That's why we have to identify the outliers in dataset. So coming to the last question, which is how is hypothesis testing utilized in A/B testing for marketing campaigns? So first, let us understand A/B testing. So A/B testing is a statistical method used to compare two versions of something like a web page, ad, or a product feature to determine which one performs better. Second is hypothesis testing. So it is a process of evaluating two competing statements, hypothesis, about a population parameter using sample data to determine which statement is more likely to be true. So this is bread and butter of modern marketing. It's how Netflix knows which thumbnail people will click more, and Amazon knows exactly where to put buy button to maximize revenue. So to explain how it works, let us use a classic e-commerce scenario. Imagine we work for an online store, uh, and currently our add to cart button is blue. So our designer thinks green button will stand out more and get more clicks. Now we can test it. So for testing, the step one is setup. So we can follow a method which is first we will set our null hypothesis. That is the color of the button makes no difference in the click rate. Then we set alternative hypothesis, which is the green button has different click rate. So second is randomization. This is the most critical step. So we write code that randomly split our website visitors. 50% of them see blue button and 50% of them see green button. So step three is analysis. So we run the test for a few days and collect the data. So let's say the green button got 5% more clicks. So is that real or is that just a random luck? So to check that, we calculate p-value. So if p-value is less than 0.05, so let us say our p-value is 0.03. So we call the result statistically significant. This means there is less than 3% chance that the result is happened by luck. So the conclusion here is we reject the null hypothesis. We have mathematical proof that the green button is better. We can now permanently switch the website to green button, knowing the fact that it will drive more revenue. So this brings us to the end. So to recap, we have seen first we learned the skeptical of correlations. Second, we weighted the risk of type 1 and type 2 errors. Then third, we used the Bayes theorem to fix our intuitions. Then why outliers can be both the problem and opportunity. Then we saw how A/B testing puts all the statistical theories into practice. So thank you for watching.